In this session, we are going to solve optimal binary search tree using dynamic programming approach. What is this optimal binary search tree? We already have seen what binary search tree is in data structures. It is one of the most important data structures which contain a set of elements where nodes in the left of the root will be lesser than the root and nodes in the right of the tree will be greater than the root. And this binary search tree is mainly focused on operations like searching, insertion and deletion. An optimal binary search tree is the one for which the average number of comparisons in a search is the smallest possible if the probability of searching each element is given. So you should be given the probability of searching each element. Only then you can construct an optimal binary search tree. The total number of binary search tree with n keys is given by a Catalan number, and this is the formula for that. C of n is equal to 1 by n plus 1 2n n. And if n is 0, C value will be 1. So in identifying solution for OBST, that is optimal binary search tree, the keys should be first sorted. So as the concept we used in binary search. In binary search, before searching for an element, we should ensure that the keys are arranged in sorted order. So the same condition should be followed here as well. So the keys should be arranged in sorted order. Then you will have the probabilities of all the keys. When these two are done, you are ready for finding the optimal binary search tree. So what tree structure will have the lowest expected cost? So when there is a cost, let Cij be the cost, be the smallest average number of comparisons, cost of comparisons made in a successful search of a binary search tree, then that will be my cost of the OBST. So if you have so many keys like AK number of keys, then all the elements which are from AI to AK minus 1 will be to the left of TK. TK be the root, and all the elements from AK plus 1 to AJ will be to the right of the root. So if we count the tree levels starting with 1 to make the comparison numbers equal the key levels, then you can frame a recurrence relation as given below. So the recurrence relation is C of Ij is equal to minimum k will take I to j, values of k will take I to j, minimum of C I k minus 1 plus C k plus 1 j plus the probabilities of summation of probabilities of I to j. So all probabilities from I to j should be summed up. So I and j will take the values from 1 to n. N denotes the number of keys. This is the recurrence relation used for calculating the cost. And there is one more feature. Cost I, I minus 1 should be made to 0. I varying from 1 to n plus 1. All the cost from I to I minus 1 should be made 0. And also the cost I to I should be made equal to the probabilities assigned to that key for I ranging from 1 to n. So this will happen when there is only one node in the tree. We will get clear idea when we move on in solving example. So in this problem, we will be constructing two tables. One is cost table, other one is a root table. So as I said, this Cij will be the formula used for finding the cost of the elements in the search elements in the binary search tree. The Cii minus 1 should be made 0. So that is why I have made all zeros here. I ranging from 1 to n minus 1. That is why if there are 4 keys, you have to construct a table with 1 to 5. and CII will be PI. So here 1 1 should be made 1. Why? Because there is only one element that serves as the root. If it is 2 2, then it will be 2 only, because that is the only node in the tree and that will be the root node. 3 3 means only 3. 4 4 means only 4, because that 1 is the only element, 2 is the only element, 3 is the only element. If that is the case, then Pi probability of that element will be the value to be entered in the root table. So we will solve a problem of OBST. So construct an OBST for the below keys. You have 4 keys A, B, C, D with their probabilities. So I'm making sure the keys are in sorted order. Yes, it is in sorted order, alphabetical order A, B, C, D. If it is not in sorted order, please make it sorted and then proceed. So we apply the same formula here. So Cij. So I is 1, j is 2. Apply the same formula. K will have the value I to j. So when k is 1, we calculate, and when k is 2, we calculate. And then of these two calculations, we take the minimum. So when k is 1, C 1, 0 plus C 2, 2 plus summation of the probabilities of 1 to 2. Here also summation of probabilities of 1 to 2. So meaning I am taking two values I and j as 1 and 2, and the probabilities of 1 and 2 is 0.1 and 0.2, 0.1 and 0.2. So in this summation I will be adding 0.1 and 0.2. That is the reason of having 0.3 here. So here also 0.3, here also 0.3. Why? Because I am adding the probabilities of 1 to 2. 1 to 2 probability is nothing but these two. So that is the reason, and I am applying the values of I, K and J here. And I will find out the minimum of all these, and my answer is 0.4. Similarly, I apply the same formula. Now I is 2, J is 3. So summation of probabilities of 2 to 3. So that is 0.2 to 0.4. That is the reason I am having 0.6 here and 0.6 here. Applying the values of I, K, J in the above formula and finding out the minimum, I will have 0.8. So when I is 2 and J is 3, K value will take the value, K will take the value 2 and 3. And similarly 3, 4 also I have to find. So like this I have to find for all combinations and fill out the table, cost table and root table. So for 1 to 2, it is 0.4. So that is why in 1 to 2 I have entered 0.4. So 2 to 3 minimum value is 0.8. So 2 to 3 will be 0.8. In the next calculation we will find out. 3 to 4 is 1.0. So 0.8 here, 0.8, 2 to 3, and 3 to 4 it is 1.0. Yes, we have entered the table. So similarly we have to enter the root values also for these value. See, in 1 to 2, where we got the minimal value, when k is 1 or k is 2. So here 0.5 and 0.4. 0.4 is the minimal value. So I got this minimal value 0.4 when k is 2. When k is 2 only I got this minimal value. Therefore, in root value for the position 1, 2 I have to put 2. So that is the reason 2 is here. Similarly, 2, 3 I have two options. 1.0 and 0.8. 0.8 is the minimum we have found. When 0.8 was obtained? When k is 3. So in root table 3 has to be entered. That is the reason 3 came here. In 3, 4, minimum value is 1. Where I got 1? When k is 3. So this is 1 and I got this when k is 3. So that is the reason I am entering 3 in the root table. So hope you understood how to fill the cost table and the root table. We will fill the remaining as well. So for 1, 3, k will take the value 1, 2 and 3, and I have to add the probabilities from 1 to 3. So that is given here, 1 to 3. So if I add 1, 2, 3, the probability will be 0.7. That is why 0.7 in all the 3 combinations, and the minimum value is 1.1. Similarly, cost of 2, 4 is also found using the same formula. And I am filling the cost table and the root table as well. So here minimum value is 1.1, therefore 1.1. And in this minimum value is 1.4, therefore here also 1.4. And I need to fill the root table as well. When I got this 1.1, when k value is 3. When k value is 3. That is why in root table I am filling it as 3. In 1, 3 it is filled as 3. In 2, 4 the minimal value is 1.4 and it is obtained when k is 3. So that is the reason I am filling 3 here. So one more entry to be filled. Apply the same formula. So cost of 1, 4, k will take the value of 1, 2, 3 and 4. Applying the same formula, we will find out the minimal value, and the minimal value is 1.7 here. So in cost table that 1.7 is filled. Now root table. When I got the minimal value? When k is 2. When k is 2, I got the minimal. Sorry, when k is 3. 1.7 is the minimum and k is 3. K is 3. This is right. The k is 3. K is not equal to 2. Therefore, I am filling the root table also. It is 3. So now I have to construct the optimal binary search tree. So what is there in this top? We have to consider that. That will be my root. So we had 4 keys, A, B, C, D. First is A, second is B, third is C and fourth is D. So here 3 means this 3 is the root node. So what is 3 as per our key value? It is C. So that is why C becomes the root node. Then I told you all the elements which are lesser than C will be in the left and greater than C will be in the right. So we have only 4. So obviously the fourth one will be to the right of C. So we can construct the fourth one, that is D, to the right of C. Now A and B has to be placed in the left hand side of C. That we know. But which one will serve as a parent? A or B? We have to identify that. So I have to compare 1 and 2 because 1 and 2 are A and B. So 1 is compared with 2. If 1 is compared with 2, what is the root? 2 is the root. Therefore, 2 becomes the parent of A. So 2 means it is B. So B comes as the parent of A. So we have constructed successfully an optimal binary search tree with C as the root, B, A as its left children and D as its right child. So here is the algorithm. So this is the initialization part we have done for the cost table with zeros and all the probabilities. And this is for root table wherein I will fill with all the probabilities and finding out the value of K in every minimal value and updating it. And in this we will be applying the formula for finding out the cost and the root value. If we use brute force method and try all tree configurations, then my time complexity will be 4 power n divided by n power 3 by 2. So these many different BSTs with n nodes can be configured. And if I am using dynamic programming, the complexity will be order of n cube.